So it searches through and finds all of those and basically places breakpoints at there and records when they're hit and where they redirect you to. So you're getting a trace of all the decision points that are relevant in the program. It's kind of an easy way to identify the basic blocks in the program. It's not completely foolproof, because if strange things are going on in the assembler, it's going to fall down. Another way that you could do this that's been implemented on other platforms is to pass it into IDA and get out, retrieve the blocks from IDA and pass that into the program and so on. But this is just a simple way of doing it. This program here, I'm just saying I want to run a block trace. So you can do it at the function level or the basic block level. In this case, it's the block level. I'm logging it to b.txt, and then demo trace is the program I'm running. This will be doing it on the function level. So the difference between the block and the function level is simply, instead of looking for flow-altering instructions, I'm looking for a more specific kind of flow-altering instruction, which in this case is just an entering instruction, which is basically a call instruction or anything that's going to go into a function or subroutine. And at the moment, it just outputs very basically an ugly trace of when decision points are hit and where they get redirected to. That's the block level one, and that's the function level one. And you can just see it's different. I'm not going to go into detail about why it's different, but obviously it's a different kind of trace. And obviously this is quite a primitive trace. You could store this in a better way and do better things with it, but just from a simple perspective, you can parse this into an actual visual graph, which I've done here. So this is the block level trace, or a portion of it, and that's the function level trace. Obviously, you can see the function level trace, a lot less going on because you're just looking at what's calling what as opposed to every single decision point. And you can do some nice stuff with this, which has been done with PyMay. I don't know if I'm pronouncing that correctly. And PStalker. And that's kind of my inspiration for doing this, really, in that you could run a run trace of a program running all the functionality you're not interested in, and then run another trace with a bit of functionality that you think might have a bug in it or that you're interested in looking at, and use basically a run trace to exclude all of the code in the second run trace that's not related to that function, that's related to normal operations, GUIs, or input, output, whatever. And it lets you zero in on the code that you're interested in. And obviously you can also do code coverage with it, because you're able to determine which sections of code have executed and therefore which haven't. At the moment, that's just a simple proof of concept. Obviously, you can use it to code a much more, put a nice GUI on it and make it a lot better, but it just shows the capability. This is going a lot quicker because I'm not doing it live. This is another little feature I've implemented, which allows you to cause malloc to run inside the process. So instead of, if you want to do stuff in the debugger, you want to actually inject code into the process, you're going to want somewhere to put that code, and this is a simple way of doing it. So what I've spawned my demo process, and I've called malloc, and I've just malloced 100 bytes within the process, and it's given me the memory address where it's malloced it. And the address format call just formats it in a nice way so we can see where it is. This can be used. I've actually got a partially working, I was hoping I was going to get it completely working when I was here, implementation that uses this to do automated inline hooking. So it will take a function call, overwrite some instructions, put in a handler so you can redirect stuff from that function call. That again can be used for fault injection, for things other than system calls, for actually calls within the process, or for doing any other strange evil things that you want to do in the process. If you actually want it to run in the process memory space rather than stop it in the debugger and have the debugger do it artificially. Oh yeah, and here's, I'm just writing a NOP instruction into the memory I've allocated and disassembling it just to show that that works. A bit of a summary of the advantages. I've kind of covered this already. In DTrace, it's good for specific solutions. It's very fast, but it can lose information. Oops. And the debugger can be a bit slower, but you get no information loss, and it's easier to implement these more generic solutions. So what my goal is to combine both of these approaches in one tool suite. REtrace has already done some work in using DTrace to do this, but development seems to have kind of stopped on that. I'm not sure if they're still working on it or not. But I'm going to try and integrate it into RSol in my own way. And then one example, the REtrace guys have got a nice set of scripts that monitor processes for stack overflows and heap overflows specifically. So rather than waiting for it to crash, you're actually proactively looking at things. And that's an example of something that you could put into a program that you're fuzzing and still have all the normal debug monitoring and so on, and have something like that on top. So that's just a simple example of how you may go about doing that. So future work, obviously I want to implement more DTrace stuff, which I was hoping to get more done before I got here, but it didn't pan out that way. And that's going to lead hopefully to metrics and better comparisons between the two, where I can actually say, okay, I've run 1,000 fuzz tests using these different methods. Which one's quicker? Which one gave you the most information, the most useful information, and so on. And actually to get some more polished working tools. The examples I've given are sort of proof of concept, really. I want to get them into a more usable state so that you can quickly get up and use them. And actually then start using it to look at Solaris security, which was my original goal before I got slightly distracted and started writing crazy tools. Few greets and props. Reached them a little quicker than I was intending. Vulndev, who basically provided me with a bunch of Spark servers to actually do this. Squidly for attempting to get a Solaris machine working for me here. She, obviously we didn't succeed with that, but she did stay up very late, so I've got to thank her very much for attempting to. LEH, you know who you are and why. And Shutzi, putting up with me. Questions and schmooballs. Yes.
Yeah, are you familiar with also systrace on OpenBSD, NetBSD, and the successes and failures in relation to your work?
Yes, systrace. I have read about systrace. I don't know a great deal about it, but if you have, information you think is pertinent, I'd certainly like to hear it. So, yeah. Anybody else? Yes.
Regarding, I guess, some of the stuff with retrace that's been done and kind of what you're incorporating, one of the biggest issues I've seen is with DTrace, the inability to do like for loops and stuff when we have large data structures, and when you want to keep those data structures in the Ruby side, that's the timing is actually affecting the process that's running. It's a large program.
Yes.
Tons of dynamic memory. I mean, I've seen, I've had real big problems trying to incorporate that all together. I was wondering if you had any thoughts of a way that may mesh together well.
Yeah.
Because I didn't see a great way of doing it within DTrace, which frustrated me. And then, being able to do it in Ruby was great, but then it was too slow, and the process wasn't really, I wasn't trying to debug it. I was trying to do it all in real time.
Yes, yes. I mean, I think that, to be honest, part of the way I've approached this is actually that maybe we don't care so much if the process is running slower when we're fuzzing. Obviously, to some extent we do, because we don't want to sit there all day while we're waiting for it. In terms of how you would fix that in DTrace specifically, I'm not really sure. I would hope that you would be able, as you say, to keep the data structures that you want in the Ruby side, but then you're facing the same problem of, if the process is waiting for you to do something, it's going to slow it down. So I don't have a clear answer for that at the moment, I'm afraid.
That was just something that I've run into, that
yeah.
if you somehow could eventually when it gets to that point.
Yeah. This is the kind of thing that I'm definitely interested in. So, and if anybody else is interested in the same issues and wants to kind of get involved, then I'm definitely interested, and grab a business card from me after or something. So yeah. Yes. It seems familiar to me, but I couldn't say offhand. But it's tools like that which I'm trying to kind of mimic for Solaris. So PyDebug and so on. Solaris is procfs for debugging, so it's not quite the same. But the same principles apply in that the bindings are, you get the bindings and then you can do it within Ruby, but it's not actually ptrace. So. No more